Log on, tune in, find out. Another good idea from Cambridge.
To introduce our first speaker for this afternoon, Jarmo Hietarinta from the University of Turku, who will talk about bilinearization and soliton solution for the ABS list.
Okay, thank you. Thank for the organizers for this opportunity. So the topic is soliton solutions for certain equations. And these equations are quadrilateral equations. And first let me give some about the notation. So the equation is defined by connecting the corners of a square, and there are many different notations for these corner elements. Some of which are included here, but there are maybe many others. Anyway, it's easy enough. All the indices indicate somehow the corners of the square. And the equation that connects the values here is a multilinear equation. So it depends on 4 variables, and it's linear in each one of them, with some coefficients which depend on some parameters p and q. They can be taught as for example, the lattice length or element p and q and so forth. Anyway, if we have a multilinear equation connecting the corners, then we can evolve this from initial. If you have a staircase like initial value, then we can evolve it. Okay, so this is the reason of choosing this particular equation. So for this equation, one can define integrability, these types of equations, by this consistency idea, which was already explained to you by Tassos Tongas in his talk. Namely that first the original equation is assumed to lie on the plane, and then you add some more equations so that if these 4 points are given, then you can calculate this, and that using the corresponding equation. And then this in 3 ways, using this equation, and this equation. And the consistency condition is that all these side equations should give the same value here. So that is a very strong algebraic condition on the equation, or the parameters of the multilinear equation. Okay, so anyway, this principle, this consistency has been used to classify integrable equations. So the main paper on that is Adler, Popenko, and Suris, who made 2 additional assumptions in addition to the consistency. Namely, there's some symmetry, which basically means that some exchanges of the parameters doesn't change the equation only by a sign. And then there's a tetrahedron property, meaning that once you calculate the x1 one term, there should be no x000 left. So this we may understand very well that this is a reasonable assumption to have some symmetry there, but this tetrahedron property was more mysterious. Anyway, they were able to do this classification, and they got a list of 9 equations. So here are those. So later in this talk, I will only discuss this, maybe the simplest list, these 3 equations. These are somehow related to the others, and then there's the main list, the Q list. And then the most complicated model, the root model somehow, is this, which has all these quartic terms, cubic terms, quadratic terms, and linear terms. And these parameters that appear in this equation are related to, are given in terms of Weierstrass elliptic functions. So it's a rather complicated equation. But it was already found a little bit earlier by Adler when he studied the Backlund's over Krichyshver-Novikov equation. So that is the origin of this model. Remember this, the classification Adler, Popek and Souris did was based on this assumption of tetrahedron property. So I tried to check whether something new comes out if we forget this tetrahedron equation, condition. Then what came out were some new equations, but they were all linearizable. So that was not very interesting. But as a side result, in this exercise, I found out a simpler form for Q4, which still depends on elliptic functions, but now it's a Jacobi elliptic functions that enter in this formulation. And there's only even terms, quartic, quadratic, and constant terms. So it's, in practice, much simpler to work with this. Okay, so now about the construction of soliton solutions to these equations. First of all, these equations have continuum limits that are ordinary soliton equations of various sorts. So since those equations have soliton solutions, these should also have soliton solutions. So the question is how to construct them. Well, there are many different ways to do this, but I will only discuss about this approach based on Hirota's method. So let's first reveal the basic idea behind Hirota's construction. The first important idea was that you have to do some kind of change of dependent variable, because the equation, it may come out from some physical principle, but the mathematical principle may require some other form, and therefore this is natural to inquire such transformation. So this idea of dependent variable transformation was came to Hirota from the idea of inverse scattering transform, because there, for example, KdV equation, the solution is given as a second derivative of a logarithmic of a determinant. So he took this second derivative of a logarithmic of something as a transformation, because then determinant is a nice, when you expand it's only polynomial and exponential. So that's a nice function. So that was the idea, and this was already in 1970s. Hirota worked most of the soliton equation. But now we want to construct discrete cases, so how to find the dependent variable transformation is the first problem. So the procedure goes like this. We first find a background or vacuum solution to the original, our original nonlinear equation. So we work on this nonlinear equation. First this vacuum solution, then a one soliton solution, and then using that we guess the transformation. There's no algorithmic. Yes, but in but in discrete cases it's not zero. So this is already a problem. Yeah. It depends on, sometimes it's zero is okay, but in the H series I showed, it's not. So anyway, we can construct a one soliton solution, and then on the basis of this, one can make an educated guess what the actual transformation should be. And then after that, using this transformation, construct a few soliton solutions first, and then guess a general form. Now, in a soliton, in a normal soliton case, these are usually Wronskians, Pfaffians, and so forth. In the discrete case, it turns out the Casoratians are the most common formal solution. And of course, John Nimmo here is an expert on these. So, so in this, as I mentioned, in the continuous case, Hirata's method worked very well because it leads to the tau functions, which are very smooth and nice functions. So now let's see in practice how this works for the discrete equations. First question, what is Hirata's bilinear form for the difference equations? Bilinear form in a continuous equation was that there was this Hirata bilinear derivative. But what is the basic principle by which this everything comes? For example, in a continuous case, it turns out the Gates idea is a good principle because it leads to the Hirata bilinear form, but also Hirata trilinear form. They all come out from a principle of Gates invariance. And here's the Gates invariance. You require that equation is invariant under this kind of change of variables. So you make this change of variables, and you should be able to pull out this Gates factor, and the equation should not change. And this is true for all equations written in terms of Hirata bilinear derivatives. Now, in the discrete case, this is the natural analog, because these x and t variables, they become discrete, like n and m, and this a and b are just some, it varies, depends on the equation. Okay, this, now in the equation itself, since discrete, we will have shifts in the n and m variables, and here are the shifts. It's bilinear or quadratic, and there are many terms. And now shift in one of the variables and shift in the other variable, their sum must be the same in each term. So also in the m, which is another direction, the sum of these indices should be the same for every term. So this is the analog. This is equation with Gates invariance. So I say this is discrete version of Hirata bilinear form. Okay. And of course we have Hirata, Dade, Jimbo, and Miwa already wrote many difference equations as well as Hirata. And if you look at them, they always have this property of this kind of invariance property, that the shifts in each of the quadratic terms, in each one of them, the shifts are the same. The total shifts are the same. Yes?
A sum of exponentials of ordinary Hirota derivatives.
Yes. If you operate with exponential of d, then it adds something here and subtracts something from there or the other. So they won't change, but you have to have, here it's possible that there's some total shift, half steps, total shift. And I don't know how is that.
It has to be sort of symmetrizable. I mean, after you change your coordinates to symmetrize it, as well as an overall shift.
Yeah. Yeah, these normally you also have the property that that the sum of these c's is 0. But just for the Gates invariance, this is all you need. And I think all the equations at least satisfy that. I don't know about the symmetrizable.
What if you shifted back in both variables by US and US?
If you shift everything, then you get a shifted equation.
Yes.
That's also valid equation.
In
but
this
the point
sum, may I ask you just for understanding, in this sum, is it just sum of this bilinear Hirota equation, is it more or less restricted sum nearby of any n m lattice point such that it is, say, finite order difference equation?
Yes, that's right.
Finite order difference sum.
Okay, so here, if we have nm here, then we can have one equation that involves this point times this point. The product of those, and the product of this and that. Product, and the product of this and that. That would still be a bilinear equation, because the sum here is 0 in this way, and the in the middle, so the average here. But another equation would be centered here, so the center of this bilinear equation doesn't have to be one of the lattice points. So I will show, there will be many bilinear equations later, and then we can see how they work. Okay, so now from now on it's just tedious work to implement this program. First, we have to find a background solution. Now we have to consider the consistency. We used the consistency idea several times here. One is the background solution. So this is the idea of James Atkinson, that we have here the cube, and the equation is consistent around this cube. So here we have the basic equation and with parameters p and q. And now we assume that the solution is the background solution is such that when we go in this direction, we get the same solution. So here we have u and u tilde, u tilde, u hat, u hat, u tilde hat, u tilde hat. And this gives us several equations because we have an equation on the sides. And these we can solve, and then the solution is the background solution. Because nothing changes, it's a fixed point in this direction, parameterized path.
This seems a little strange, Jarmo, because you normally think of this direction as being the vacuum transformation. So the vacuum transformation should
yes,
take
it is too, but now we assume that because before we can start, we have to have a background solution. So the background where vacuum just repeats, background repeats. We'll use the same cube to get the one soliton solution as well, but this is sort of the starting point. Because we have to have first the vacuum solution, and it's not 0, usually. So this means that we have to solve these kind of equations, where this would be the u hat, but it's the same, and this is the parameter of the vacuum solution. So let's take this very simplest equation. It's h1. Okay, so here is the hat, and if you consider that hat is nothing and q is r, you get this equation. And if tilde is nothing and p is r, then you get this. So these are the side equations. On this side, here we have that. No, on the front you have this equation, on this side you have that equation. So we have to solve this equation to get the background solution.
So is it a special value of r then?
No, r is arbitrary.
You know.
But the requirement that we get no change when we go up, or some trivial change, this is the constraint that makes it the background solution as opposed to some more general solution. Now this is of course not a very complicated equation, but to make it even simpler, let's parameterize this so that we can take the square root of this. So we change from this original parameterization of this equation p and q to some other parameters a and b. And if we do that, then they factorize. And now, so we have this, we want to solve this, but if something product is 0, then one or the other factor can be 0, and they can even alternate. So what we really have is to solve these kind of equations where this is could be a function of n and n, and this as well. but in fact consistency requires that this only depends on n and this only depends on m. And then these are the solutions. These are possible background solutions now. Yeah. And well, these are rather bad backgrounds. They don't lead to interesting results. So we only take this background solution. So now we use the same cube, but now this will now be a actual soliton solution here. So this is maybe called K, a soliton parameter, or kappa. Okay. So now we have to solve these equations, but here we know that this layer at the bottom is the background solution. So this will be the background solution. This is the tilde of background solution. This is hat of background solution. These are the one soliton solutions. It's the new one soliton solution. And here is its parameter. Okay. So now to solve this equation. And the idea that was discussed in this paper was that we take this one soliton solution to be of some constant, the background part like this, with this is a new parameter related to this kappa, and this d, and if you make this substitution and require that there's no constant term here, then you have this kind of relationship. So we have converted the equation to be solved into this form. And then this has to be solved, and we convert it to a matrix equation. So this is in terms of V. Write V in terms of F over G, and then introduce a vector. And then you can write this equation in terms of matrix equation, where the matrix is just composed from this. And here you get G1H. So we have this matrix equation to get from phi, which is the one soliton solution, get one step to the n plus 1, and this to n plus 1. And if we have the 0, 0 value, then we can repeat this to construct the nm value. But since these are simple matrices, it's easy to construct a phi nm as this kind of product. And then we convert back to V. But now we notice that n and m appear only in these kind of nice ratios, or these. So this is somehow the main ingredient in all what that follows. This kind of rho and m, which is power of these kind of ratios, where a and b are the parameters of the equation, as described before. So now we have the one soliton solution. V in terms of rho. And this is just like in the Hirota's method. Rho is exponential. And if you think about this, this is a discrete version of the exponential.
Is the discrete version of the exponential associated with V-type algebra? So you'd expect to get back in
I think this is just a standard KdV type thing that you get here. Because the phase, this is only the exponential factor. The phase factor is just like KdV.
But I think, for example, in Hirota-Miwa, you get simple linear factors, not rational factors.
No, you get less rational factors in Hirota-Miwa, yeah. In the R. In fact, there's a little bit more freedom there, I think. No, this is precisely, but this is a simpler form of Hirota-Miwa factor, I think. But we can discuss this later. Okay, so let me just recall that this was the equation we went to solve, and then we make this kind of substitution to get a nice form for V. V is a new unknown. Then this was solved, this matrix method. And then we get the form which is somehow similar to the standard Hirota one-soliton solution. And here's then combining all together. This is our one-soliton solution. So here we have the background, which is linear in the spatial variables. Which
it is only one soliton solution.
One soliton,
yes.
yes.
But one soliton solution should not be associated with complete integrability.
No, it's not enough. But now the structure of the solution gives us an idea of how to proceed further. Okay, so this is the form, and this is our substitution, and these are the tau functions. And now, so all this one soliton exercise gives us an idea of how, for this form, the bilinearizing transformation. Okay, so here we can see what, well, the additive bit can be slightly changed, but this suggests certain kinds of structure for the G and F. Okay, so anyway, now we can forget what was before and take this as our starting point for bilinearizing. So substitute this, and this happens. This is what happens. So this is the equation. Now I substitute this into here. I should get shifts of G and F, and I can combine them so that one term contains H1, which is bilinear, and another H, and then the H1 will be just this, and it's written in this strange way. But if you notice the product of this times that, it's cancelled from here. So this vanishes if H1 and H2 are 0. Okay. Now let's look at this H1 and H2 equations. So H1, we have the lattice, and then which terms do we have here? G tilde times G hat times F tilde. So we have this kind of product. Then we have G tilde times F hat, this kind of product, and then F also, and then we have product called F and F hat tilde. So this kind of. So this means that the sum, index sum in each term is 1. There's always 1 tilde and total of 1 tilde and 1 hat in every term. So it's a Gates invariant. Here also, but here they are arranged differently. Here, same thing, but organized slightly differently. So these are both Gates invariant, and but it has the additional property that if you remove all the tildes and hats, it's 0. So this is the like a derivative. So if you expand this, you only get derivatives. If you take a continuum. Okay. So the result is that we could bilinearize equation H1 using these bilinear equations as given. So now we have done the bilinearization. Next step is to construct the multi-soliton solutions for these equations. Then they automatically solve this using this ratio. So now at this time, we have to introduce Casoratians. So we have some functions which are indexed by I, which is the soliton name, N and M, which are the lattice variables, and H, which is some kind of shift. Okay, and we make first a column with different solitonic parameters, and then we arrange the columns by different shift parameters. So this would be like a Wronskian if the shifts are just right. But since this is a discrete, it's called Casoratian. Here's a typical example. We have a shift parameter 0, 1 to n minus 1. And if we only write down the shift parameters, we get this. And then this is a further condensed notation introduced by Nimmo.
What is Casarati matrix?
This matrix here. You make these columns with different soliton names, and then this matrix with different shifts. That would be a Casoratian. But we only use this kind of organized shifts by one. And take the determinant of that matrix, then that is
I can understand. Every phi is a
column. Yeah, every phi contains is a column of phi I. So this is the soliton index. So one function for each soliton. Yes. And then make long columns with different solitons. But we also need shifts which correspond to derivatives. Because in Wronskian we have derivatives, in Casoratians we have shifts. But the shifts, now we can operate what kind of shifts we can have. And here's one is that we have, I will give the functional forms soon, but we can have shifts like integers, and another is shift like integers, but skip the last one, or the last one is shifted by one more than here, so it's slightly different shift, but only the shift is different, last shift. Okay, so these are two of the ingredients, for example, but you can have other kinds of shifts. Yeah, so here is the function I'll be using. Index I is the soliton name, n and m are the variables, and h is the shift. Okay, so this is the result then, that if we have this h1 equation, make this kind of substitution and these kind of parameters, then we can express this in terms of these h1 and h2. And it turns out that I can choose this f to be the Casoratian n minus 1 tilde, and g to be this Casoratian, with these kind of entries in the matrix.
So these psi's were with you for psi sub?
They are the phi's that were before. Sorry for the notation. So exactly. So in all the columns are just different powers here. 0, 1 to n minus 1 in F, 0, 1 to n minus 2 n in the other matrix. And then soliton 1, soliton 2, and so forth. And the square matrix, so if we have a 2-soliton solution, we only need 2 by 2 matrix. So in a 2-soliton solution, we will have something like phi 1 n m 0 and phi 2 n m 0. And then in the F case, we would have here phi 1 n m 1 and phi 2 n m 1. And this would be F. And if we would take the G, then for G, we would put here 2 instead of 1. That's the only difference. And then you take the determinant, and this only means that we add some extra k in some column.
Is there some compatible continuous evolution in which G is the derivative of F?
Yeah, this is the idea, because normally this would be the derivative, but if you take the total shift of F, then it's very difficult to handle any kind of Laplace expansions. So it has to be a shift in one column only. So it takes some time to work out the details, but this should go to the derivative in the
I
limit.
guess it's a continuum limit in some sense.
the continuum limit should be derivative because the continuum limit of this is KdV.
But I mean, just one continuum limit, not both of them. If you just take continuums in hat, for example.
Yes, then you get some semi-discrete form, but I'm not sure about that. If you take the continuum limit in both, then you of course get KdV. Okay, so this is what comes out of H1, which was the simplest equation. Now the other equation is already much more complicated because there's some quadratic and linear bits, and so.
Before you go there, is it obvious that when you take the continuum limit, that the soliton solutions also become the
Yes.
soliton solutions?
Yes, because remember the ingredient was this rho factor, which rho nm, which was in the construction, and this just goes to the exponential, e to the x times something plus t times something else, if you take both limits.
But what's the analog of the g on f?
Yeah, so this what we were discussing, this should be the derivative of f prime of fx over f, probably. But
Oh, so
I'm
it's
not
potential
sure.
KdV.
Yes, this is potential KdV, exactly.
Where do you take from such non-symmetry of two different directions like x and
That's
t?
right.
Here you have something very, very
That's
symmetric.
very,
Yes, that's some
good observation. Of course, this
Yes.
makes it more fun because this is totally symmetric. So how
Yes.
can we get KdV out? Well, the limit has to be asymmetric. And what you can do is the limit will depend on some epsilon small parameter, and you have to adjust it so that the x goes like epsilon and time goes like epsilon cubed or something, so that you have 3 derivatives of x and 1 derivative of t combining, and all the previous powers somehow cancel. It has been done, and I
can
could
be
do
done
it.
partially. So-called discrete KdV obtained by first by Sergei Monakov, but Moser later with this so-called discrete KdV with one time but discrete x.
Yeah, Frank maybe has
Yep.
that.
It is done, yeah.
Yeah, or intermediately.
Yeah, they are
Intermediate limits. So
Yeah.
you did
Well,
okay.
collaboration of people.
Okay, somehow. Okay.
Yes. It's just somehow amusing that this gives KdV, which is so asymmetric, but it does indeed. The next one is, what is the continuum limit of this? This is some extra bits to the KdV from this, but I don't remember what it was. Okay, now this is a little bit more complicated because of this thing. And if you parameterize like this and you do the calculation algebra, it turns out that the one soliton solution has this power 2 of the linear bit as the background. Just turns out that way. So previously we only had one linear bit, and now we have a power 2 for this equation. So you can also see that if you just take this and that, some powers are there. But anyway, this is what happens. And the calculations are rather straightforward, so I will not give them here. And the one soliton solution, remember we made this U bar, 0 and so forth, and the D equation, the matrix equation. It's quite algorithmic. So when you just do the machinery, you find out this as your one soliton solution. Again, here's the linear background, squared should be here. And here's the raw term once more, which becomes the exponential. But now we have a little bit more complicated, and for this k is explicitly here. So this is just a little bit more complicated form. But rather straightforward to derive. But okay, so now it becomes a mess. because make this kind of substitution where here are the tau functions. They are f, g, h, and s. And somehow in this form we need all of them. And f is this. And g is just one shifted. And s is, h is with this shifted. And s is with this last one shifted. So need two derivatives more or less. But you have 4 of these Casoratians here with different shifts. That's the only difference. But they are not very much different because, for example, you can show that h minus s is f times the sum of the squares of the okay. Anyway, you substitute this into the H2 equation, you collect terms, and it turns out that these bilinear equations appear there. And if these are solved by some Casoratians, then everything is fine. And indeed, these f, s, and h, they do solve all these. And it's usually, to prove that such things solve equations, you have to use the Laplace expansion of matrices. And then it comes out like this. You get quadratic expansion. And again, these are bilinear in the sense that these all have the same number of shifts. And here also, and here. But this is rather strange, only tilde shift is needed, but it's related to that as well. Anyway, now here if you put remove the shift, this vanishes. But here also, but the arrangement is slightly different. Because here we need single tilde, single hat, and both with some different thing. But anyway, one can show that the Casoratians described here do solve this, and then we have bilinearization. But it's not in any way a neat result, because we need so much. But maybe one can find some further relations between those.
Did you say what the continuum limit was? Or you asked?
No, I asked if Frank remembers the continuum limit of this.
Well, yeah, we have a list for open beam.
But this is KdV with some extra bits.
Then they're all kind of degenerations of Krichovanovikov equation. Different degenerations of the elliptic.
Different nonlinear extra as compared to KdV. Yeah. So, okay. And here's the explicit form. So remember I said that I can express everything in terms of these 5 bilinear equations. And here's the expression. H2 is phi times p, and the coefficient functions are these. Okay. Doesn't carry any information except that I did my homework. Okay. So this is the last equation. I'm going to consider H3. This is, if delta is 0, this is which KdV? So much?
Potential modified.
Potential modified KdV. If delta is 0. And delta not being 0 adds an extra constant term there. Okay. So now just the recipe is already given. So first we take this equation and put it in the cube like this, assuming that these are the same. That would be the background solution. So if you do that, then, for example, if you remove the tildes, then you get this becomes that, and this becomes that, and then this becomes that. And if you remove the tildes, then you got tilde parameter r, then you get that. So anyway, we have this equation. Now, these look like some kind of curve, ellipse. Elliptic. It should be parameterizable by sine and cosine or that sort of thing. So we propose writing u in terms of a times some new function, b times e to the minus some new function. And furthermore, for these parameters p and q also reparameterize like this. Then this leads to the factorization again, and you can solve the equation, and you get this as your solution. So these here turn out to be powers like this, and this A and B, the product must be related to minus R delta over 4, and R is this parameter, and delta is the parameter of the equation. So this is the background solution. Notice that now the background solution is a power type, not a linear one. So this is just its structure is like that. Okay, so this is the background solution with alpha and beta, which are the essential parameters here. They are related to the parameters of the equation, like the lattice parameters. Then the construction of the one soliton solution is also algorithmic, and there will be the soliton parameter kappa somewhere, and there will be these rows. So this will come out of this machinery. And of course there's the background part, and then some extra bits with some coefficients here, so that they don't factor out. Okay, so this is the result. But this is not a very neat form, so I think we have to change parameters once more to get this into the form that we previously had. So here's the reparameterization. Alpha squared is minus A minus C, A plus C. Beta squared is this. Kappa squared is that, which correspond to changing P and Q into that form. So this is, as a result of this change, rho gets this nice form, as before. So now we are somehow in the previous formalism. Rho looks as before, and then we have a change between from P to A and from Q to B, and A and B are now, in our sense, good variables or parameters of the equation, not the original ones. Okay, so this with this rho and the above A and B, one soliton solution, we guess the bilinearization. So what is it? It is, here's the first part, and here's the second part. And now notice I have here F bar over F, and here F down bar over F, with this as before. So it's now parameterized in terms of one F, which is the usual one, but there's this bar shift, which is not part of the construction otherwise. So this is the bar shift is the shift in the soliton direction, sort of. And now we have to change the psi, of which are the ingredients of the matrix, with this kind of thing. So C plus Ki and H. So the bar shift is in terms of this H, here and here.
So you mean it's every index is shifted up or every index is shifted down?
Yeah,
Yeah.
which is annoying. Yeah.
This lives essentially in a three-dimensional.
Yeah. Yeah, you can interpret it. The third dimension is the soliton dimension or something. Well, not really, but yes, you have to extend the space. You can think it that way. Okay. Now again, if we make then this substitution given here to the equation, then the equation can be given in terms of a bilinear equation, at least two ways. One is in terms of these two equations, which have one shift in either tilde or one hat, and then symmetric shift in delta or bar, or one that has one shift of each in every term, or one shift up in tilde and hat and one down bar, or neutral in bar but one tilde and one hat shift. So this is what I mentioned, that there are different kinds of shifts. You can have same equation in center at various points. Only if you have two shifts in one direction, you can pull them down by overall shift. But this is one shift up, one shift down, and neutral. And we need those three equations. And the continuum limits probably go to 1. Or at least it's possible. So it's bilinearization in terms of this. And now the F was already given, so it's now a matter of proving that this is that they solve this. But this looked like these Hirota Miwa equations, especially these. This is the Hirota's equation, I guess. And these are slightly shifted somehow from all those. Okay. So, have you seen this? It seems that these Kasaratians, they solve many equations because of the shifts can be slightly different. Whereas in a continuum limit, derivative is a derivative, but here we can split the point in several different ways. So the discrete shift, there can be several discrete shifts that go to just one derivative. So this is the multitude problem here. Okay, so now I'm in time, I suppose. So what I have described here is the construction of multi-soliton solutions and bilinearization for quadrilateral lattice equations in the ABS list. I showed you only the H series. Q1 has been done. Q2 is almost there because it's also a very complicated equation. Q3 and Q4 we have not applied this, but there exist other results there. For example, the n-soliton solution has been derived from Q3, but it's from another way, namely from this Quispe-Capel equation from the 80s. And it's related to Q3 in some way, and using this relationship, then it was derived in this paper. And Q4, remember that this was using elliptic parameterization. So solving that would require elliptic functions everywhere. So this is still not done. In principle, there's some procedure to, but it's not explicit in the sense of Kasaratians or anything. Okay, thank you.
Concerning these multi-soliton solutions which you found in this work, in case of, so you have the X-time discretization of KdV, yes? Is it possible to present, I would say, pseudo-physical picture of multi-soliton solutions like was theory of soliton started, like two solitons moving, phase shift, interaction, and so on. This is a natural question to your
yes.
pseudo-physical interpretation
Yes,
of
absolutely.
your results, yes?
Yeah.
Might be important, yes?
Yeah, but see, this rho, which carries the n and m index, and n and m become x and t in some way. So this rho is the exponential factor.
Yeah.
So in that sense, if you plot this, you would get some discrete version of a solid. But there's this background thing is spoiling somehow. Because, well, the background can be 0 if delta is 0 in some of these equations. But in, like in potential KdV. But in some other special cases, we get this constant term, and the corresponding soliton, continuous soliton equation will also have this thing. And then you have this strange background, which is really proportional to x plus t, or x and t, linearly proportional. So it's like some tilted surface.
It might be also interesting interaction of soliton even in continuous case in such non-trivial
could be, yes. Yes. So in that sense, we have to do the continuum limits also very carefully.
That is would be natural just to
Yeah,
find
yeah.
just beautiful physical presentation of
Yeah,
that.
I would say so.
We have done something like that for
Yeah,
the
this is-
ultra-discrete case, actually.
Already did.
Yeah, well, I think for the two soliton solution.
For two soliton.
Yeah, yeah.
Of course, most important first case, two soliton solution. Will be multi-soliton solution only pairwise interacting system, or maybe this picture is more complicated in
No, I
discrete
think
case also.
the idea that each interaction is pair interaction, but the triple interaction must be like a young Baxter type of thing, must be a combination of pair interactions.
How factorized?
Yes, yes.
Yeah, this is in a sense the same question. I mean, is there some notion of an initial value where you can see solitons propagate, and is there the analog of them being reflectionless potentials for some kind of linear operator?
Yeah.
It's really asking whether the structure that we know from a continuum is also present for soliton solutions of that. For this
If
kind
you
of
think
soliton
about the
solution.
initial value problem, then it's a little bit different, because here, of course, we do have initial value problem on a staircase kind of initial value. But remember that the continuum limit is a skewed continuum limit, so it's really hard to see how it goes to the usual continuum initial value problem of the continuous case.
So in particular, there is no natural linear operator associated.
Well, we have
where you
lag
deal
spread.
with reflectionless potential.
That I don't know, but
There is
we have the
lag
lag
spread.
spread. Lag spread.
There is like
Yeah, there is lag spread because
Yeah,
of
but
the
is
consistency.
this interpretable in the Hilbert space so that you get initial values that lead to reflection being absent?
I don't know.
You probably need to rewrite the Lux pair in some kind of scalar representation probably to identify it as such.
But it has not been done. I mean,
No.
should be some analogs.
Well, it's
Maybe not
equivalent
quite
to
clear.
the,
Yeah.
the discrete Schrödinger spectral problem in some
Okay.
sense.
Well, that is the case, for instance, in TODA.
You can always
But,
rewrite in
is it
that
true
form.
here also?
Well, it's
And what is it? What sort of
usually,
operator is it?
usually more like Volterra equation. All these equation except for Q4 can be mapped into the Volterra equation.
Well,
okay,
the
so-
Volterra equation is relative of
The
TODA.
one of the
Which is
second
also
one
known
of the
as
soda
Custom
hierarchy
Rubik.
when one of the field is 0.
Perhaps we should continue this conversation over coffee. So that we can
No, Volterra means discrete KDV. It is same
Yeah,
different countries use different terminology.
Thank you.
But there is linear.